lesson, it's going to be a bit of a mishmash of a lot of things because we've got a lot of content up to now that we can cover, okay? But the point of this is that we're going to use our compound angle trigonometric identities to solve essentially equations and problems using these things. That we've got more skills than we've ever had before, and we're going to solve them. All right, let's get on to it. So the main ones that we're going to be looking at are these ones, okay, which are related to all these ones down here. So these ones down the bottom that I'm highlighting now will become very, very important. And of course, this is just our HSC formula sheet, isn't it? Okay, so it's a HSC formula sheet. I'm just going to rub these off because we're going to refer back to it real soon. Okay, now we're going to solve this problem. Okay, so I'm going to use an identity for, let me read the question out. Solve sine 2x minus sine x equals 0. So it's a trigonometric equation. The issue is that we've got two different angles, all right? But luckily, this one is a double angle. And we have a lot of double angle identities. And just by the way, that should be that. I don't know what that is there. And they all stem from this one here, these two here, even this one here. And the one we're going to use is sine x and x, because that will equal sine 2x, x plus x equals sine x. So we're replacing these things in there, just in case you don't remember how we did it. So that's what I'm going to use. Sine 2x, and our identity will be 2 sine x cos x. If you don't believe how I get it, do finish off what I was doing in the formula sheet. Okay, so I'm going to use that. So I'm going to go 2 sine x cos x minus sine x equals 0. Okay. Oh, and I'm going to make these inclusive because that might make it nicer. Now, I know that both terms have a common factor of sine x, so I'm going to take that out. So I'm going to go sine x, then I get 2 cos x minus 1 equals 0. Now, using the null factor law, all right, I'm going to divide both sides by 2 cos x minus 1 and then by the same thing, okay, I get sine x equals 0. And when does sine x equal 0 between this domain? Well, it actually equals 0 at 0 and at 2 pi, okay? And that comes from our sine wave, which starts at 0 and finishes at 2 pi there, okay? Now, also using the null factor law, if I get rid of that, if I divide both sides by sine x, I get rid of that, sine x, that's still 0, okay? The second thing I'm going to get is that 2 cos x equals 2 cos x minus 1 equals 0. Therefore, cos x equals a half, all right, if we just rearrange this equation. Now, when does cos x equal a half? We've got these triangles in our formula sheet as well, and that's 2, 1, root 3. That's 60, that's 30, and obviously that's 90. So cos is adjacent over hypotenuse, and so it looks like that's adjacent, that's hypotenuse, so it looks like our angle, the related angle, is going to be 60 or pi on 3, which is because we're in radians at the moment, so x equals pi on 3. But we have to use all stations to central to find our second solution. So we know we have a solution here because cos is positive, but there's another solution here. So because that's 0 and 2 pi, and our related angle is pi on 3, and that's pi on 3, our second solution will be 2 pi minus pi on 6, which actually happens to be 5 pi on 3. And that should be a 3, by the way, because our related angle was 3. I don't know why I wrote 6. that would be 30 degrees if that's the case. Okay, so what's our final answer? I'm going to do a little box here, and I'm going to write it. Therefore, x has many solutions. It has 0 and 2 pi and these ones, so I'm going to put them in order. 0, pi on 3, 5 pi on 3, and 2 pi. Awesome. Okay, so we're using our compound. In this case, we use double angle, which is very important to solve these trigonometric equations. All right, let's graph this one. Okay, so what I'm going to use for this one is this identity here that says cos squared x is equal to 1/2 plus 1/2 cos 2x. So because of this 2, you guessed it, it comes from another compound formula. If we put in x and x here, you'll get it. But you can see it's the same equation as this one down here. So have a look at it, okay? I don't have time to get into the nitty-gritty of it, but we've done this in the past. Okay, so I'm going to graph, instead of thinking about graphing that, I'm going to change it to graph that. So I'm going to go y equals 1/2 plus 1/2 cos 2x. Now, what does a constant do for any function? Well, all it does is that it moves it up or down, okay? So in this case, it's moving it up by 1/2. Okay? That's good. All right, so instead of the graph, let's start drawing it. Instead of it being here at 0, it's going to move up to 1/2. So I'm going to go 1/2. And we're going to have a line there. So essentially we're going to have the graph going up and down there. Okay? Now, there's a couple of other things. The number in front of this tells us the amplitude. So how high it goes up. So the amplitude is 1/2, so it goes up 1/2 and down 1/2. All right. Now the amplitude is like the wave. How high does the wave go? How low does the wave go? So in this case, it's telling us it's 1/2, and so it's going to be 1/2 up, 1/2 down. So it goes from this blue highlighted line up 1/2, so that's up to 1/2, and down 1/2, down to 0. Okay. There's one more thing we've got to look at when we're drawing trigonometric graphs, and it's the number in front of the x, which is n, and it helps us find the period. So the period is for cos and sine will be 2 pi over n. In this case, our n is 2, so our period will be 2 pi over 2, so it will be pi. Now, what is a period? It's how long it takes us to complete a full wave of this function, all right? So normally it takes us 2 pi to get there. Now it's going to take us pi. So I'm going to put that in. I'm going to put pi, and then I'm going to put 2 pi here. I'm also going to put halfway between them because it's going to help me draw it. Pi on 2, and this is 3 pi on 2. I think I'm ready to draw it. Cos always starts up the top. It doesn't start at the origin. And so it will complete a lap back at the top there, and a lap back at the top there, and it will complete a lap there. About halfway through, it's going to cross there. So, and now let's do it. So, and it keeps going as well as this side. There is a negative component, and remember that this is x and this is y because that's the realm that we've been presented with. Okay. All right, so that's using these trigonometric identities to help us draw a graph. All right, let's see what the next question has in order for us. All right, so this is a proof, okay? So I'm going to be using cos 2x. Cos 2x is so powerful, all right? But I'm getting ahead of myself. What I'm going to do is that this is a proof. So normally we have left-hand side and right-hand side equal to each other. In this case, I'm going to choose right-hand side because that looks pretty neat and I want to try and get it to tan. Now I'm just going to write a few hints for myself. I know that tan equals sine over cos, okay? So I'm going to use that knowledge. Now, because of that, I can see that this cos 2x, and it's powerful, and if I look at my formula sheet, these are all cos 2x, all right? So if I multiply both sides by 2, I get rid of the 2 at the bottom, and the 2 moves over here, so I end up getting 2 sine squared x equals 1 minus cos 2x. And this next one down the bottom, I'm going to get 2 cos squared x is equal to 1 minus cos plus cos 2x, all right? And then obviously I need to move these guys over to the other side. So that's what I'm going to do over here, okay? So let me write out what it is. Okay, so remember, beautiful working out starts with writing at least part of the question out. Now I'm going to substitute in for these cos 2x's. Now, because I'm going for tan, I want to get something in terms of sine at the top and something in terms of cos at the bottom. So let me do some working out here. I know that cos 2x is equal to cos squared x minus sine squared x, okay? So, and I need it in terms of sine, so I'm going to replace this guy using our Pythagorean identity, okay? So that's 1 minus sine squared x, bracket minus sine squared x, so I'm left with 1 minus 2 sine squared x, which is what I was pointing out to you over here. That's a version of it, okay? Now, for this one, I want to change it to a cos, so I'm going to use this same thing, except instead of replacing the cos, I'm going to replace the sine. So let me do that. So I'm going to go cos 2x is equal to cos squared x, so I'm starting with this guy again, minus 1 minus cos squared x. Now, if I'm really careful how I ski jump at all, I end up getting 2 cos squared x minus 1. Now, what I'm going to do with that is I'm going to replace these two things in for these two things. So let's do that. 1 minus bracket 1 minus 2 sine squared x over, getting ahead of myself, 2 cos squared x minus 1. Oh, I did definitely got my ahead of myself. So I'm going to move that across to there. I'm going to put my line. I missed out on this guy, so I'm going to put that guy in there. And that's our substitution there. Now, I'm going to rearrange a few things. 1 minus 1 will cancel that out. That negative is going to, the double negative there is going to make it positive. So let's do that. 2 sine squared x over. Now we have a similar situation here. 1 minus 1. So we're left with just 2 cos squared x. Now this is wonderful because we've got sine squared x over cos squared x. Bingo, that's what we want. That equals tan, so it equals tan squared x, which equals left-hand side as required. Okay, so that is just like doing any kind of proof. And one more example to go. All right. So I'm going to use this double angle formula for sine 2. Let's read the question. Given cos x equals 5 over 13. This just means, okay, that's interesting. So it's in this quadrant. Okay. That's what it means. From pi on 2, it's in that quadrant. So only sine is positive. Okay. And given this situation here, I'm going to immediately write its double angle formula, which is 2 cos x, 2 sine x cos x. All right, I was going to write cos x first, doesn't really matter. I have cos x. Cos x is 5 over 13. What I don't have is sine x. But I can get it from using Pythagoras. If this is x, cos is adjacent over hypotenuse. So this will be adjacent, this will be hypotenuse. So I need to find this one here. By using Pythagoras, so x is probably not a good pronumeral, I need to find opposite. So I'm going to go opposite equals the square root of 13 squared minus 5 squared. Now that just equals 12. All right. So if that's 12, what is sine? Well, sine x is equal to 12 over the hypotenuse is still 13. Okay. So given one of it, we can find the other. And now I can substitute this and this into this whole thing. So therefore, sine 2x equals 2 times sine x is 12 over 13 and cos x is 5 over 13. Now there's just one caveat. We're in this quadrant here where only sine is positive. So because this one's the cos, I'm going to put a negative in front of that, which is going to make the whole thing negative. So if we put this in our calculator, we should get 120 over 169. So what is the value of sine 2x given all that information? Negative 120 over 169. Hopefully this helps. There's a lot of information, but it's just how we can use trigonometric functions within, trigonometric identities within trigonometric equations. Peace out.